Welcome to This Explainer. Today, we're diving into a brilliantly structured proposal that completely reimagines municipal infrastructure. We're going to explore how to take everyday municipal waste, things like wastewater sludge and organic bioscraps, and transform them into high ROI renewable fuel and fertilizer. And look, this isn't just some theoretical environmental concept. It's a highly detailed revenue-producing economic engine. Okay, let's dive into this. For decades, cities have basically looked at municipal wastewater sludge and local food waste as giant disposal burdens, right? They're seen as liabilities that cost a ton of money to treat, transport, and throw in a landfill. But what if we completely flipped that script? What if that sludge is actually a trapped asset, just packed with recoverable energy, carbon, nitrogen, and phosphorus waiting to be monetized? Well, today, we're going to show you exactly how to unlock all of that value. Before we get into the really cool mechanics, let's quickly establish our foundational premise, the circular bioeconomy. In the context of this specific facility, it means taking the waste inputs a city is already producing and running them through an integrated biological system. We extract energy as renewable natural gas, or RNG, we recover nutrients using algae and cattails, and we produce clean, treated water and commercial-grade fertilizers. Literally nothing is wasted. The whole shebang becomes a product. Here's a quick roadmap of where we're headed. We'll systematically cover the revenue engine, the algae-cattail filtration loop, smart harvesting and drying, the winter operation strategy, and finally, we'll compare two investment pathways. All right, let's kick things off with Section 1, the revenue engine. Let's move through this and see how it builds. Our process starts by blending nitrogen-heavy municipal sludge and local organic waste with carbon-rich cattails, which, by the way, are harvested right from the facility's own treatment ponds. This blend is fed into an oxygen-free anaerobic digester. Inside, microbial communities go to work breaking down that organic matter to produce raw biogas. That biogas is then cleaned and upgraded into pipeline-quality renewable natural gas. But the leftover liquid, known as digestate, doesn't just get tossed. It actually becomes the vital fuel for our next major stunt. Now, here's a massive detail you absolutely cannot miss. By co-digesting that sewage sludge with the harvested cattails, we stabilize the carbon-to-nitrogen ratio inside the digester. Research actually shows this specific combo can boost biogas production by roughly 50% under favorable conditions. To be safe, though, this proposal models a very conservative 40% captured production uplift, accounting for things like storage and handling. That is a massive financial impact on the overall ROI, just by intelligently balancing the feedstocks. But hey, the biological process is really only half the battle, right? We have to ground this back to the bottom line. Making RNG is fantastic, but for this to be incredibly profitable, that gas needs to qualify as a renewable transportation fuel under the EPA's Renewable Fuel Standard. Securing Renewable Identification Number, or RIN, credits is absolutely essential. The proposal is crystal clear on this. The economics heavily rely on these credits, and honestly, the project shouldn't even proceed to full build-out unless this highly lucrative fuel offtake pathway is locked in. Moving right along to Section 2, the algae-cattail filtration loop. You can't just dump raw anaerobic digestate straight into an algae pond. It's way too turbid, too dark, and too heavy in free ammonia. It would block out the sunlight and completely choke the algae. So this facility includes a vital pre-treatment step. By running the liquid through a specialized settling tank first, we remove those heavy suspended solids. We're effectively clearing the smog. Then that clarified liquid flows into engineered ponds. And a quick note here, these ponds use engineered clay or composite liners. That's a huge deal because it protects the groundwater, drastically reduces permitting risk, and makes public infrastructure review a whole lot smoother. Now, growing algae, that's relatively easy. Actually making money from it? Famously difficult. As the source material points out, historically, one of the critical challenges in achieving an energy return from microalgae is harvesting and concentrating the algae. Drying the harvested biomass is also a highly energetic process. Basically, algae is incredibly dilute. Pumping all that water, skimming it, and trying to boil off the moisture will usually absolutely obliterate your profit margin. Which brings us to the innovation in Section 3, smart harvesting and drying. Instead of harvesting the algae on some rigid, inefficient timer, this facility uses actively managed, sensor-based monitors. These smart sensors track everything in real time: turbidity, chlorophyll A, pH, dissolved oxygen, temperature, light penetration, and biomass density. A mechanical skimmer is only triggered when the algae reaches optimal harvest conditions, or when it starts blocking too much light. This keeps the algae in a highly active growth phase, prevents bloom crash risks, and most importantly, it drastically reduces the sheer volume of water you have to send to the centrifuge. And this brilliantly illustrates how we solve the drying problem. After the centrifuge, that concentrated algae slurry and the harvested cattails need to be dried out. But instead of burning expensive fossil fuels to do it, the plan uses a retrofitted 40-foot Connex shipping container transformed into a solar kiln. It traps solar heat using double-layer glazing. But here's the kicker. Underneath those drying beds is a phase-change material called erythritol. It melts during the day, absorbing massive amounts of heat, and as it crystallizes at night, it releases it. It acts like a giant thermal battery that slashes purchased energy costs. All right, on to Section 4, the winter operations strategy. A huge question with any biological system is, what happens when it gets freezing cold? Well, this facility is designed for year-round profitability by shifting between two distinct operational modes. During the warm months, it relies heavily on biological growth in the algae and cattail ponds to strip nutrients. But during the cold months, when pond productivity drops off, the digester just keeps churning out that profitable RNG by using the stockpile of dried cattails we stored up all summer. It's a completely seamless transition. But what about the liquid digestate produced in the winter? Since the ponds are way too cold for the algae, the facility bypasses them entirely. Instead, it utilizes an advanced chemical precipitation process. By adding magnesium chloride and using zeolite ion exchange, the facility recovers up to 99% of the phosphorus and up to 92% of the nitrogen directly from the liquid. This creates a standalone, highly concentrated winter NPK fertilizer product that adds an estimated $225,000 in net value every single year. All right, Section 5. This is where we bring it all together. Two investment pathways compared. Let's start with Pathway 1, our lower-risk algae fertilizer and biostimulant model. In this scenario, the dried algae is tested and sold as an agricultural biofertilizer, completely avoiding the complexity of biodiesel. Looking at the cash flow, the RIN-secured RNG is the undisputed heavyweight, pulling in over $2 million annually. When you add the cattail co-digestion benefit, the algae biofertilizer sales, and that winter NPK fertilizer, you're looking at a robust, diversified net cash flow of nearly $3 million a year. Now, what's really interesting here is Pathway 2, the algae biodiesel model. It uses the exact same base facility, but instead of selling the whole algae as fertilizer, we extract the lipids to create liquid biodiesel. The remaining def-fatted algae is still tested and sold as a fertilizer co-product. This pathway definitely adds engineering complexity because you need extraction, fuel handling, and storage equipment, but it allows the facility to tap directly into liquid transportation fuel markets. So why does this matter? Let's look at how they stack up side by side. Pathway 1 requires a capital cost of roughly $8.46 million. Pathway 2 jumps to $10.96 million because of all that lipid extraction equipment. While Pathway 2 is incredibly innovative, Pathway 1 actually offers a faster, simple payback of just 2.82 years, compared to 3.72 years for Pathway 2. Pathway 1 also boasts a massive 15-year ROI of 431%, with a net present value of over $22 million, beating Pathway 2's 303% ROI. Pathway 1 simply yields a higher overall return because it avoids those hefty initial capital costs. Now, you might have noticed we haven't talked about carbon credits yet. Throughout this proposal, the financial pitch is kept strictly conservative. Carbon credits are entirely left out of the base ROI, so we don't overpromise. But make no mistake, this facility is a carbon-accountable powerhouse. By tracking RNG combustion, the biogenic carbon captured by the biomass, displaced fossil fuels, and avoided landfill methane, this framework offers massive, verifiable environmental reporting value for any city striving for net zero goals. Which brings us to our final thought. We've seen how smart engineering, from anaerobic co-digestion to thermal battery solar kilns, can turn a city's waste liabilities into a multi-million-dollar asset. The economics are incredibly clear, the payback periods are remarkably short, and the environmental benefits speak for themselves. So the provocative question you have to ask your decision makers isn't whether you can afford to build a circular bioeconomy facility. The real question is, what is the cost to your city of not upgrading your municipal waste into revenue-producing infrastructure? Thank you so much for joining me on this explainer. Keep learning and keep asking those big questions.